Hello and welcome. I am Durai Kannan. I'm here to talk to you about the world of solar energy and its evolving technologies. Energy security and energy independence offered by solar power along with solar hybrid inverters could change the way solar power is used. We'll begin with an introduction to solar power, how it is harnessed, and maximum power point tracking or MPPT, a crucial technique that ensures solar panels operate at their highest efficiency. Next, we'll take a closer look at solar hybrid inverters, devices that intelligently manage power from solar panels, batteries, and the grid. You learn about their various modes of operations, including grid-tied, off-grid, and backup modes, and how they adapt to different energy needs. Finally, we'll explore the applications of these systems in homes, businesses, and remote areas, showcasing how solar hybrid technology is making reliable and renewable energy more accessible than ever. So let's get started. This presentation is about solar hybrid inverters, which empower you to manage your own power efficiently, sustainably, and profitably. We'll begin with an overview of solar power in India, which shows untapped solar power potential in India. According to a report by the Council on Energy, Environment and Water, over 25 crore households across India alone have the potential to deploy 637 gigawatt of solar energy capacity on rooftops. This report also highlighted that just one third of this residential potential could support the entire electricity demand of India's residential sector. As of March 2025, India's cumulative rooftop solar capacity reached around 14.9 gigawatt. As of June 2025, India's total installed power capacity has reached approximately 476 gigawatt. Out of this, thermal around 240 gigawatt, about 50.5%. Renewable energy sources, including large hydro, around 226.9 gigawatt, approximately 49%. In these renewable energy sources, solar 110.9 gigawatt, wind 51.3 gigawatt, hydro 47.9 gigawatt, biomass-based small hydro is the remaining one. Nuclear around 8.8 gigawatt. Solar inverters are the brain of your solar system, transforming raw solar energy into usable electricity. Let us look into the choice of solar inverters, starting with grid-tied inverters. Currently, grid-tied inverters remain the popular choice for many, largely due to the attractive return on investment they provide. While grid-tied inverters have served us very well, the time has come to question if they truly meet our evolving energy needs. Grid-tied inverters export the available solar power directly to the grid. Power is not stored. Your solar panels, when connected via a standard grid-tied inverter, cannot provide power during a grid outage, and the available solar power simply goes unused. Already, India is facing excess power around noon and shortage in the night on days when generated solar power is high. If this trend continues, there will be excess solar power around noon and on more days. This power cannot be used. This can also lead to grid instability. Another choice of solar inverters is hybrid inverters. So, how do we address the issue of unused solar power during grid outages faced in grid-tied inverter? A far better choice is the solar hybrid inverter. It gives you the crucial ability to store the surplus power when it is abundant, and then utilize this stored energy precisely when solar generation is low or unavailable. Further, hybrid inverters look more attractive due to the fact that lithium-ion batteries prices are falling, leading to improved return on investment. Beyond these crucial advantages, the inherent flexibility of hybrid inverters unlocks a host of additional benefits that we'll explore in the coming slides. Solar power generation. Solar panels generate electricity through the photovoltaic effect. When photons from sunlight strike the semiconductor material in the solar cells, electron-hole pairs are generated. Due to potential barrier of the p-n junction of the solar cell, these holes and electrons can move in only one direction, leading to a DC current. The voltage of a solar panel is intrinsically determined by the semiconductor junction properties of its solar cells, while the current generated is directly proportional to the incident solar irradiation. An inverter is used to convert DC from the solar panel to 230 volts AC, which is required for the utility purposes. Let's have a quick look at the solar cell, which forms the core of a solar panel. The solar cell is made of P and N type semiconductors, forming a PN junction. When light falls at the junction, electrons are dislodged from some of the atoms, forming hole and electrons pair. The electric field at the junction is such that the hole moves to the p type and electrons move away from the junction. A load connected to the metallic contacts collects the current. A glass panel lets the light pass through while protecting the cell mechanically as well as from harsh outdoor environment conditions. The equivalent circuit of the solar cell has been shown here. Solar cell acts as a current source. When the solar irradiations fall, the current source is activated. The voltage of the solar cell is decided by the semiconductor characteristics. How the PN junctions form, what materials used, semiconductor material used to form the solar cell. One cell voltage is about 0.45 volts to 0.55 volts when connected to a load. It's for a silicon-based cell. So many such cells are connected in series in a solar panel to get more voltage. So solar panel is formed by connecting many such cells in series, shown here. These cells are connected in series to form a higher voltage at the solar panel terminals. The output current will be of the current in weakest cell in the series of cells. So if one cell is weaker, the same current has to flow throughout. So all the cells will carry only the weakest cell's current. Bypass diodes are used to circumvent this problem. Suppose this cell is weak, this cell can provide much more current than this, as well as the other two cells can provide much more current. So this current will bypass through this diode, and the higher current of the healthy cells will be the output current of the solar panel. One of the solar panel characteristics is shown here. X-axis is voltage, Y-axis is current. At zero voltage, that is the panel short circuit conditions, current at 1000 watts per meter square irradiation is about 2.7 amps. At zero current, this is the open circuit voltage for different irradiation levels. It ranges from 19 to about 21. And the current drops as the irradiation level goes down. So this is the PV characteristics for one radiation, solar irradiation. X-axis is the voltage, Y-axis is the current. Zero voltage, that is when the panel is shorted, the current will be short circuit current. Again, this is the open circuit voltage. The current is zero. The power will be zero in both cases because either current is voltage zero here or current is zero. So the power is voltage multiplied by current is zero. As the voltage increases, the current remain almost same. So the power, which is voltage multiplied by current, increase linearly until a point where the current drops steeply. So at this point, we call it maximum power voltage, and maximum current is maximum power current. We get the maximum power from the solar panel. The converters are operated such that the solar panel voltage is a maximum power voltage to extract maximum power from the solar panel. One of the solar panel data sheet has been shown here. This is of a Wari 400 watts solar panel. This is one of the models of these solar panels around 400 watts. We have a power voltage, maximum power voltage, maximum power current, and short circuit current, open circuit voltage, and the module efficiency shown here. This is a standard test conditions values, and this is normal operating condition of temperature. These are values here given. And let's look at only these values of normal operating condition. The maximum power is 296.8. The maximum power voltage is 34.7. And then maximum power current is 8.55. And short circuit current is 9.08. And then short circuit voltage is, open circuit voltage is 42.1. And the panel operates at this efficiency. There is the power in the solar irradiations, the percentage of power in the solar irradiation converted into electrical power is the efficiency. And the other solar panel details, mostly mechanical, have been shown there. We need solar inverters. DC solar power is converted to AC by inverters. This conversion is necessary as all appliances use AC voltage for their operation. Inverters can also push power into power grid. Inverter system monitors system performance as well. Different types of solar inverters. String inverter. Solar panels are connected in series to form a string. When panels are in series, their voltages add up while the current remains the same. This creates a higher DC voltage that's more suitable for the inverter. The converter AC power is then either used by the loads within the property or exported to the utility grid. String inverters don't work without a power grid. If one panel in a string experiences a reduction in current production, example, due to shading, dirt, or defect, etc. It acts as a bottleneck for the entire string. Since the current must be same throughout the series circuit, the output current of all other panels in that same string will be pulled down to match the lowest producing panel's current. Bypass diodes or optimizers are used to mitigate this problem. Microinverter. The microinverter typically mounted under each solar panel takes the solar DC output and converts it into AC power feeding to the grid. In microinverters, defective or shaded panels do not affect the power delivered by other panels. Central inverters. Central inverters typically have power ratings ranging from hundreds of kilowatt to megawatts. Several strings may be connected in parallel in a combiner box, and these strings are fed to inverter, to basically a very large inverter. Inverter types based on functionality. Start with the grid-tied inverters. These are the most common type of inverters. Their primary function is to convert the DC power generated by solar panels into AC power that is synchronized with the utility grid's voltage and frequency. They are designed to feed solar electricity directly into the public grid. These grid-tied inverters won't be operational if there is a grid outage. Off-grid inverters. Unlike grid-tied inverters, off-grid inverters operate independently of the utility grid. Their main function is to create their own AC grid, supplying power to connected loads from the solar panels. A battery is charged by solar power when it is available and provides power to loads when the solar power is not available. They manage charging and discharging of batteries. Hybrid inverters. These are versatile inverters that combine the features of both grid-tied and off-grid inverters. They can connect to the grid, charge and discharge batteries, and power home loads. They can manage power flow between solar panels, batteries, the grid, and the home. This comparison of the inverters we just saw features string inverter, off-grid inverter, hybrid inverter here. Grid connection, string inverters, yes. Off-grid inverters, no. And partially the grid is used to charge the battery here. But solar power cannot be exported in the off-grid inverter. Hybrid inverter, yes, grid connection is there. Battery support, no for string inverter, yes for off-grid, and of course yes for hybrid inverters. Backup power, no, yes for off-grid and hybrid inverters. Application, grid-tied, residential or commercial. Off-grid inverters for remote and no grid conditions. Hybrid inverter, residential, commercial, grid-tied with backup. Let us go a little bit deep into solar hybrid inverters. One possible solar hybrid inverter system is shown here. This is a solar panel, a boost converter, inverter, and a bidirectional DC-DC converter and battery. This boost converter boosts the solar panel voltage to 650 volts DC bus, which is also regulated. An inverter provides a three-phase AC voltage from 650 volts DC bus. Also, there is a bidirectional DC-DC converters. The DC bus can charge the battery through the bidirectional DC converter. Also, the battery can be discharged back to the DC bus and to the load through this bidirectional DC-DC converter. The boost converter takes power from the solar panel at maximum power point using an MPPT algorithm. The MPPT algorithm works in the voltage range of 200 volts to 650 volts. Beyond this voltage range, the power available itself so less, the MPPT algorithm is not required. Let's see the power flow scenarios in this system. When the solar power is strong, the solar power flows to the DC bus and to the load through the bidirectional inverter. Also, the battery is charged from the DC bus through a bidirectional DC-DC converter. If solar is weak, the solar power flows this way. Battery discharges to the DC bus. Both together can supply the load. Another scenario is when solar power is weak or no solar power and battery state of charge is very low. Battery cannot provide power. And at these circumstances, the grid power through the inverter, bidirectional inverter, it charges the battery through the DC bus and the bidirectional DC-DC converter. Let's see the modes of operation the solar hybrid inverters can operate. To start with, strong solar and grid power available. The solar available power from solar is high because of strong solar. Okay, first let's see what are the things connected to the solar hybrid inverters. This solar hybrid inverter, solar panel is connected. Then backup loads. These backup loads can be lighting loads, fan loads, computer systems, modems, etc., which require backup. Then the solar hybrid is connected to a battery and also to a grid, and in the same line other home loads also connected. So when available solar power is high during the strong solar times, the solar power first charges the backup loads, gets power from solar, and then it charges the battery, and more power is there, it will go to other home loads, and still more power is there, the power can be exported to the grid. In this case, the solar is strong and grid power is not available. So the grid is open here. Additional to the earlier connections to the solar hybrid, there is another priority loads have been shown here, which can be connected to the solar hybrid inverter. So the backup loads are very essential, which have to be backed up all the time. The priority loads can be one inverters out of one air conditioners out of many, which can be chosen as a priority load, which has more priority than the other home loads. So the power flow goes like this. The solar provides power to backup loads and charge the battery. If the SOC of the battery is more than certain level, which can be programmed by the users, the backup priority loads also supported. Then still there is a power, then other home loads can be supported. If solar power is less or there's no solar power, but if the battery is full, In that case, the solar power battery together provides power to backup loads first, then it might provide to priority loads depending on the state of charge of the battery. It can be programmed. Still power is there, it might provide to other home loads. Sometimes it may be advantageous to export power through from battery also. That time it can be exported to grid also. That depending on the user's preference. So the solar is weak, and battery, you can see the battery capacity is low. So now the solar power plus grid power, they provide power to backup loads first, then for battery charging, and then to the priority loads, and then other home loads as well. When grid is present, all loads are serviced. Backup loads, priority loads, other home loads, battery charging. Only the whatever available solar power is used, the rest of the power come from the grid. But if the solar power is weak, and if grid is not available, if it is open, and even the battery is also low, there is a facility to connect generator to the solar hybrid inverters. So generator will provide the power along with whatever available power from solar panel. They provide power to the backup loads to charge the battery to power the other home loads. Factors to consider when choosing a hybrid inverter. Power rating, match to your peak load. Battery compatibility, ensure it works with your chosen battery chemistry, lithium ion, lead acid, etc., and voltage. Number of MPPT trackers based on number of strings the hybrid inverters can handle. Each string can separately the maximum power can be derived from each string separately. Efficiency, higher efficiency means more usable power. Monitoring and communication features, this makes using of hybrid inverters very easy. And you can also exploit the maximum potential out of the hybrid inverter. Warranty and support, safety certification, and scalability also be considered. Advantage of hybrid inverters, uninterruptible power. Solar hybrid inverters, when combined with battery storage, access a seamless backup power source. The event of a grid outage, they can automatically switch to drawing power from the solar panels and or the connected battery, providing continuous electricity to essential loads. This is a core advantage over traditional grid-tied solar systems that shut down during outages. Energy security. A household or business becomes less vulnerable to grid fluctuations, blackouts, and potential geopolitical issues affecting grid electricity supply. A more resilient and reliable energy source. Advantages of hybrid inverters. Energy independence. Hybrid solar inverter can go entirely off-grid if the option to integrate with a wind turbine is provided. This will ensure continuous power without grid even during long spell of rainy days. Even if the hybrid solar inverter doesn't directly take wind input, a dedicated wind charge controller can feed power into the common battery bank that the hybrid inverter manages. likely to pay back as the battery price is falling. Cost of lithium-ion batteries, a key component of solar energy storage systems, has been decreasing over time. As battery prices fall, the initial investment for a solar plus storage system becomes more affordable, which in turn shortens the payback period. The payback period could further be reduced if facility to sell excess power back to the grid when the energy price is high. This will be likely during night time. This graph shows the price of power energy for throughout a day. This was got from Indian Energy Exchange. This is the graph shows for 2 days on May 26, May 25 and May 26 in 2025, the energy price for different time of the day. Starting from 12:30, 12:45 a.m., the energy price is high because there is no solar energy generation. The consumption is still high, and price falling here. Maybe during this time, even though solar energy generation is not there, consumption could have reduced. Again, after morning 6:30, 6:45, prices starts falling as solar energy generation increase. And during around 9 o'clock to about 3 o'clock, where the solar generation is maximum, you can see the cost of power is almost 0 per unit. Again, after 3 o'clock, the solar power generation gradually reduces. But, the price also increasing. Again, you can see after 7 o'clock, there is no solar power generation, and also the consumption is increasing considerably after 7 up to maybe 12, and the solar power is going very high, and to the extent 10 rupees per unit. So by using a hybrid inverters, one can charge the battery when during the availability of the solar power from about 9 a.m. to 3 p.m. That can be exported when the power price is very high, maybe after 10 or 9 or 9 to 12. There is another possibility also exists here. Even if solar power available is less in the particular location, during this time, the battery can be charged from the grid. The power is available for a very low price, and this stored power can be exported between 9 and 12 p.m. the night when the solar power price is quite high. That way we can it can be very much profitable. Applications. Residential homes, ideal for homeowners looking for energy independence and backup power. Small businesses or offices, ensures continuity of operations. For remote cabins of off-grid locations where grid connection is unreliable or unavailable. Areas with frequent power outages provides crucial reliability. Maximum earning by exporting power when the price is very high. Presently, this facility is not available. Individual or small solar power generators cannot export power with a differential costing mechanism. It should be possible in the future as more solar power, grid-tied solar power is generated in the daytimes. The things will get worse, and probably one will get that opportunity to sell power when the price is maximum. Provision to connect to wind turbines will enhance continuous power availability. There could be a little or no need for grid power. Advantages of hybrid inverters: increased self-sufficiency, reduced reliance on the grid. Energy bill saving, optimize consumption and utilize cheaper energy. Backup power or resilience, essential during power outages. Grid independence, flexibility in energy management. Future proofing, easily integrate batteries later. Reduced carbon footprint, streamlined installation. One unit handles multiple functions. Thank you. Feedback, especially critical one, is very much welcome to this email ID. Thank you.